Know my associates, the rest of the blue team there. So an outline for the presentation, we'll go over some background and theory, steady state, step response, frequency response, root locus, proportional controller, proportional integral, and conclusion. And really this presentation's more about the proportional integral controller, and the rest of the stuff will just be past information that you've probably already seen. Here's the voltage system. It's a 5 horsepower, 3-phase motor, coupled with a DC generator. It's hooked up to a set of load lights and a power supply there on the right. Here's a block diagram and the step response, input-output graphs there. Here's a graph of a constant input for the voltage that we did way back in probably week 2 at 75%, which is the upper range of the system that Mitch ran, and that's where this presentation is focused, geared around. Here's our SSOC, very interesting, as you can see. The lower range here is Andrews. Then you have, I guess, low middle would be my range. Then you have John's range, which is 50 to 75 maybe, 50 to 70, and then Mitch's 75 or 70 to 90. And you can see the strange slope there in my range, how it gets steeper. Here's a step response at 50 to 65. Yields an output of around 7.8 volts or so. Here's a step down, and you don't need to care about that. Here's a step response model. There's a step down model, and here's some results that we drew from our step response, T naught, tau, and K values for the different ranges. This was pre-Mitch, I guess, before he migrated over to our wonderful group. And here's a frequency response graph, 65%, 2 hertz. Here is Bodie for Mitch's range. Got FU, KCU, K, all the conclusions you can draw from a Bodie plot there. Amplitude ratio, that's actually Andrew's range up there, I guess. Here's the phase model for Andrew's range. You can see where it crosses 180 right there. That's FU. And here are the conclusions with Mitch added in for the frequency response. Yeah, you can read those if you want. Okay. Here are the symbols that we're going to use for the proportional integral slides. KCD, critical dampening, is at 0 degrees. KC at 500, 45 degrees. KC at 10, 70 degrees. KCQD, which is quarter decay, that's 78, and KCU at 90, which is the ultimate, or FU. Here's a root locus for the 70 to 90 volt range. I don't have the angles drawn in on this graph, but they are coming up. Here's the proportional root locus results for our system. If you want to read those, you can. Here's a chart for the proportional root locus results that we got. It's very pretty. Thank you, Mitch. Here is some more results for the proportional model that we did, which was these graphs here. If you remember those graphs, I didn't put them all in. But there are the results. You can see KC at 500 in the 70 to 90 range is monatomic. And at KC at 10, it was oscillatory, as well as the ultimate and critically damped. Or quarter decay. Here's a experiment for the proportional only. It's got a step up right there at about 10 seconds. And it looks pretty good. Here are the results. Part of the results for Mitch's range there. I think we already looked at that. There we go. 45 degrees, 70 degrees, 78, 90. You can see the different values there for KC in the outline boxes. Okay, for the proportional integral experiments, we didn't have all of our information in on time, so we're just going to look at the 70 to 90 volt range. There's a table for a K value of 2.0, a tau of 0.1, T naught of 0.04, and tau sub I of 0.13. There's some graphs of the experiment. Here's the rest of the graphs. And here's a graph of wind up and wind down, which is it's what you get out of proportional integral controllers, as you can see there. And they're the way to go.